Work done by expanding gases. Here we have a cylinder with a gas in the region here. At the moment the piston is at a height h1, giving a volume v1. If we raise the piston to a height h2, we now have a volume v2. The piston has risen by a height delta h, which would be given by h2 minus h1. If the pressure remains constant, the expansion being due to a temperature rise, the work done by the gas will be equal to the force exerted multiplied by the distance moved in the direction of the force, in this case delta h. Or we can say that the work done is equal to the force times h2 minus h1. But we know that pressure is equal to force over area, and so force is equal to pressure times area. Also, h2 is equal to volume 2 over the area of the piston, and h1 is equal to volume 1 over the same area of the piston. So we can substitute in for these expressions, getting the work done being equal to the force, which is pressure times area, multiplied by the change in height, which is v2 minus v1 over area. Cancelling the areas gives the work done being equal to the pressure multiplied by the change in volume. Just to stress again, this requires the pressure to remain constant. If we plot a graph of pressure against volume, we went from volume 1 at a pressure P to volume 2, also at a pressure P. The area is equal to pressure times the change in volume, which we've just shown is equal to the work done by the gas on expanding. If a compressed gas is released and expands without being heated, the pressure will drop as the volume increases, and we might get a pressure against volume graph going from volume 1 to volume 2, something like this. The work done will still be given by the area under the pressure against volume graph, by this area. So this is how we could work out the work done. Here's an example. A cylinder of gas at 3 megapascals and a volume of 0.2 cubic meters is released into the atmosphere at a pressure of 100 kilopascals. Assuming the gas is at a constant temperature, calculate the new volume. Well, for this we can use the ideal gas equation, and we can arrange it that P1 V1 over T1 is equal to P2 V2 over T2. This is explained on the video on the ideal gas equation. But T1 is equal to T2 where till the temperature doesn't change. So we can rearrange for V2 being equal to P1 V1 over P2. Putting in the figures, the pressure one was 3 megapascals, the volume of 0.2 cubic meters, and the pressure at the second instance was 1 times 10 to the 5 pascals. This gives a new volume of 6 cubic meters. Assuming the pressure drop is linear as the volume rises, calculate the work done by the gas on expanding. Well, for this we can draw a pressure against volume graph, and the pressure goes from 3 megapascals to 0.1 megapascals, with the volume going from 0.2 cubic meters to 6 cubic meters. And we can assume a linear drop like this. The work done will equal the area under the line, which is this area. The area is given by the average height, which is 3 plus 0.1 over 2 megapascals, multiplied by the width of the shape, which is 6 minus 0.2 cubic meters. This gives a value of 8.99 megajoules of work done by the gas on expanding.